Um, two comments. Number one, uh, Bemet, I just want to thank everybody who's joining in on this. Steve Frankel and I have known each other for a bunch of years. This is really my first opportunity to try to create. I would ask everybody to mute themselves if they're not if they don't want to speak. Steve and I have known each other for a bunch of years since he was a faculty member in the United States, and we first started talking about Aliyah. And Steve, you've been here, what, 8 years, 10 years? Long time. So I will take just a little bit, like a 0.5% credit for Steve and his family being here. The credit is really all his, but it's a thrill for me that he is here in Israel. And I will tell all of the Machon Lev people that are joining us now, I want you guys to understand, and I'm going to say it because I want it to come across from my perspective, but Steve, you can fill in. Steve is an absolute superstar scientist who has more than just a warm spot for Machon Lev. He wants to help us. We're very much on the same page in terms of the importance of creating high quality academic activity in a religious environment. And I think that's the place where we're coming from today. Steve has a strong track record from his professional research career in computational fluid dynamics. There was a point about a year ago where we even talked about Steve coming and helping us at Machon Lev in terms of our general high performance computing activities. I think what happened was both disappointing then, but just a little bit of siyata d'shmaya in terms of how these things work out. Instead of spending part of his sabbatical year with us, Steve has just finished a sabbatical with a company in Tel Aviv that maybe I'll tell you a little bit about, but the punchline is a very simple one. Steve has offered to share with us some of his experience and insight into both the science and the potential applications of quantum computing. And on that basis, I envision his presentation to you today to really be one of, let's stimulate some ideas, let's get people thinking, let's get people to a point where this new technology, which let Steve speak about, is something that we as a research community at Merkaz Akademi Lev can already start taking advantage of, both on our own initiative, each person in his own discipline, but at least in some of them with Steve's guidance and help. And that's really where we're at today. And I'll just add my disclaimer, because I have to go to pick up my wife at the airport, I'm gonna drop out at some point and ask somebody, Yoram, can I ask you to take over as host? You're muted. Yeah. Okay, so I will at some point make you host, and that way you will control both the discussion and the share screen stuff and whatever else comes with it. Steve, hamon hamon todot, thank you very, very much. And I've only taken 3 minutes of your time, so you're ready to go. Go for it.
Okay, thank you, Chaim. Let me share my screen if that's possible.
Should be.
Let's see how that works now. Okay, and
there we go. Great.
See if I can go to full screen. Let me minimize. Okay.
Yeah, you're there. You're there.
Okay. Great. So thank you, Chaim, for inviting me to meet with you and your esteemed colleagues, and thank you to all the colleagues for joining. The plan was, as per Chaim's request, a 30-minute or so presentation overview, and then a discussion. So I tried to limit myself, and feel free to interrupt, and some of the slides will go quicker than others, so I'll try and keep us on pace. I'm from New York, so I can talk pretty quick, but I realize that the objective is to have a discussion. So anyway, this is called A Brief Introduction to Quantum Computing, and it's motivated not only by my interest and the sabbatical that I just finished, but a new grant that I was fortunate enough to receive from the Israel Science Foundation, the Ministry of Defense, with a couple of colleagues at the Weizmann Institute, called Hybrid Quantum Algorithms, or HiQA, which is an acronym I made up, Integrated Software and Hardware Implementations in Science and Engineering. And this is an opportunity to discuss what that's about and how perhaps we might be able to work together, going forward. So let's go to the quick outline. So I'll start with just a brief introduction about myself and my interest in quantum computing, and then we'll get into some basics of what is a quantum computer, and leading to quantum algorithms, and then my grant, what's it about, and what potential collaborations we could explore. So by way of introduction, there'll be a lot of infographics in this presentation. They're easy to find on Google, and it's just a lot easier than preparing all the graphics yourself. So you'll see some of those. All the credit goes to Google and the internet. So what do I know? First of all, what's a background in quantum computing? Very little. I'm not an expert. I'm not an even expert in my own field, let alone this field. But I did get interested in this field about 10 years ago, a little over 10 years ago, when I was at Purdue University. I was there for 20 years. And a paper came out, which I'll mention a little later in the talk, around 2009, which caught my attention. And I got into the field. I collaborated with a colleague who actually got his degrees at Hebrew University. His name is Sabri Kayes, who's a professor in chemistry at Purdue. And we recruited a highly motivated and very smart graduate student, Yudong Cao, and did some nice work and published a paper that's pretty well cited to today. Yudong went on to co-found and is the CTO of one of the hottest startups on the planet, Zapata Computing. And he was also patented algorithms. I didn't know you can do that, but he's done that. And I had one other student who I want to give a shout out to, Rishab, who we were able to publish a nice physical review paper. But again, that was it. And then we made Aliyah, and I could not find any Israeli colleagues to give me the time of day to collaborate in quantum computing, because I'm a mechanical engineer. So. Is that okay? Can we still hear me?
You're fine. You're good.
Okay, great. So I'd say I don't know very much, but maybe I know a little bit more now. As Chaim mentioned, I just finished a sabbatical working at a startup company named Quantum Machines. It's probably the biggest startup in Israel in the space. A really impressive company founded by 3 PhDs from the Weizmann Institute in physics. And I also was fortunate enough to get this grant. And I wrote the proposal 2 months into the sabbatical, and it got funded 2 months before the sabbatical ended. So I like to say that if you look in the dictionary under sabbatical, you'll see a picture of me for the ideal sabbatical, because that usually doesn't happen. So I'm get a lot of personal satisfaction from that achievement, but now obviously we have to do the work. So, okay, so what is a quantum computer? I guess the founder of quantum computing, at least conceptually, was Richard Feynman, a fellow Jew, who said nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. So that's Richard Feynman kicking off the field back in the 80s. So what is a quantum computer? Let's just jump right to it, because I was fortunate enough to take a TUL in December 2020, a couple months into my sabbatical, to my now co-PIs at the Weizmann Institute. This is the superconducting qubit lab of Serge Rosenblum, a young up-and-coming professor and a super nice guy at Weizmann. And this is a chip. This is a superconducting quantum chip, and it sits actually inside a dilution refrigerator to cool things down to just a few degrees colder than outer space. There's a lot of hardware that controls these qubits, and one of the components is this box here, which you see, which has QM on it. That's the box that Quantum Machines makes to control these qubits. And so they're like a middleware between the software, which we program at a regular computer, as we'll talk about in a few minutes, and the hardware, which is these qubits. And then everything is, controlled as best as possible by these large, expensive refrigerators. So formally speaking, a quantum computer is defined by my new friend, Jack Hidari, as also a fellow Jew, it's a device that leverages specific properties described by quantum mechanics to perform computation. And Jack is somewhat famous for running for the mayor of New York back in, I think, 2013 or something like that. He ran as a Green Party candidate. He didn't get too far, but he's like number 3 or 4 at Google. So he's a pretty serious player. And he published a book a couple of years ago, and he's got a second edition that just came out this month, which I'm planning to teach from next semester if everything goes well. So the fundamental unit of quantum computing are called qubits, right? In classical computing, they're called bits. Classical bits are either 0 or 1 through transistors where the current is flowing or not flowing, for example. So you have 2 states. But qubits are unique in the sense that they're based on a 2-state quantum mechanical system, and they can be in 0 or 1 or any linear superposition of the 2 states of 0 and 1, which is kind of a weird thing to say, but that's the nature of physics and the way Hashem built the world at really, really small scales. So you can have a qubit in state 0 or qubit in state 1, or you can have a qubit as represented by this vector in this sphere, which we'll talk about in a few minutes, which is a superposition of the states 0 and 1. The only problem is when you actually so when you're doing the computation, you get 2 for the price of 1, so to speak, right? You have a single qubit, you have two states that you can compute with. But when you go to measure the qubit and see what the output is from the calculation, the way nature works is the wave function collapses, so to speak, and you end up with either 0 or 1. So there's an advantage and a power in the quantum state, but the output data is only a classical state of 0 or 1. Now, quantum superposition is something we can take advantage of for quantum computing. An additional property of quantum mechanics that we take advantage of is called qubit entanglement or quantum entanglement, where you have 2 qubits and you can entangle these qubits, so to speak, for example, by shining a laser on them. And once you do that and these 2 qubits are entangled, changes to 1 qubit can affect the other qubit, even if the qubits are separated by large distances. And so this is really funky. This is what Einstein called spooky action at a distance. We don't understand it, but it seems to be the way the quantum world works, and why not take advantage of it for quantum computation? So these are the quantum mechanical properties that we use to exploit and do quantum computing. So what is a qubit? Continuing the discussion, let's look at it from a mathematical point of view. The state of a qubit is represented as a 2-dimensional complex vector. It's usually given the symbol psi. And instead of using the arrow on top or a boldface, which is what we typically do in linear algebra or in math and engineering, in physics and quantum mechanics, we use Dirac notation, which is the so-called ket notation, where we put the symbol of the vector inside this vertical line and this right-facing bracket, and it looks like an arrow. So you just have to get used to it. But this is just simply a column vector, and you remember it's a column vector because column begins with C and ket begins with K. Ket column, so that's how I remember it. And the general state of a qubit can be in a superposition of the 0 state and the 1 state. And the coefficients that pre-multiply these states are alpha and beta. These are in general complex numbers. So this is a 2-dimensional complex vector. And alpha is actually related to the probability. It's called the probability amplitude for the 0 state, and beta is called the probability amplitude for the 1 state. And the idea is that the amplitude alpha, the magnitude squared, is the probability that when you measure the state of this qubit, you get 0. And beta squared magnitude is the probability that when you measure this qubit, you'll get 1. Remember, when we measure the qubit, we collapse the wave function, we only get the classical state 0 and 1. And so this gives us the probability here. And again, this is called the wave function. And the laws of probability, this is called Born's rule, say that the sum of the magnitude squared of the amplitude has to be equal to 1. Both alpha and beta are in the 2-dimensional complex space. So we can represent this as a column vector, as we said. We can write it as alpha beta, where alpha is multiplied by 1, 0, and beta is multiplied by 0, 1. Again, this is the definition of the so-called computational basis states. This is the 0 state, as we showed it here, and this is the 1 state here. So again, this is a ket. This is what we just talked about. Now, you can also have what's called a bra, which is basically the conjugate transpose of the ket, and it's written in this fashion using Dirac notation. And so you can see the definition of a bra is you take the ket and you do the conjugate transpose. So wherever there's an I, you flip it to you change the sign of the imaginary part, and of course you change it from a column vector to a row vector. And so you can see that here and here. And of course you can put these together. You can do, for example, inner products of a bra and a ket, and then you get a bra ket, which is bracket, and that's why it's called bracket notation. And so here you can see things we've talked about already with the superposition. There are other superpositions you can have for specific values of alpha and beta that are specifically labeled. For example, this is the plus state and the minus state. And then you have the I state and the minus I state as well. These are example qubit states. And these can all be nicely visually represented. A single qubit state can be on what's called the Bloch sphere. This is the Hilbert space of the two-dimensional complex vector space that we're dealing with here. And on the Bloch sphere, the quantum state psi is represented as a vector. So the 0 state would be the north pole conventionally, and the 1 state would be the south pole. And then a general superposition state would be represented by a vector ending its point on the surface of this sphere, and given by, in this case, 0a plus b1. And this can also be represented in polar notation as well, where you have the theta and phi angles that describe this vector. So any vector on this sphere that ends at a point on the sphere is a superposition state, and these are what are called pure states. Okay. So while the qubit is alive, you have these states to compute with, but then when you measure the qubit, you end up with only a classical state. So here's an illustration. There's lots of these on the internet. I just like them. They're pretty. And here's a couple of the states that we mentioned before, the plus state and the minus state on the axes of this sphere, on the equator of this sphere. So what is a computation? A computation is basically changing the quantum state. You do something to the quantum state to change it. So here's an example of changing the quantum state from a 0 to a 1 state. Okay, and if you can do this precisely, then you're doing computations. And of course, these qubits are noisy, as we'll talk about, and so you may not end up exactly on the 1 state, and that would be an error in the calculation. And so typically, quantum error correction is needed to fix that. And partly the reason why the qubits have to be cooled down to outer space temperatures is to minimize noise and these errors. And here's just one more of these just to show, again, here's the 0 state and the 1 state, and here's the superposition. And then on the right is the application of something called the Hadamard gate, which we'll mention in a second, which takes you from the 0 state to the plus state. And then if you started at the 1 state, when you apply the Hadamard gate, you go to the minus state. Okay, so I mentioned this gates. So quantum computing is done by changing the state of the quantum of the qubit. Okay, so this is what quantum computing is all about, just simply changing the state of the qubit. And a quantum computer is built from what's called a quantum circuit, an analogy with classical circuits, which contain wires and elementary quantum gates. And these gates are basically operations that we do to the qubit to change its state from one state to another. So let's see here. So first of all, quantum gates on a single qubit can be described mathematically by 2x2 matrices. These have to be unitary matrices in order to maintain the probabilities, the sum of the probabilities to be 1. But 2x2 matrices times a column vector, very simple linear algebra. So linear algebra is the bread and butter math that you need for quantum computing, which is actually nice because most of us are comfortable with linear algebra. Here's some example single qubit gates. This is the Z gate. You can see it's a simple 2x2 matrix. And this is the Hadamard gate, which we mentioned before. So for example, if you started with a qubit, a superposition state shown here, and you applied the X gate, you basically flip the 0 state to the 1 state and the 1 state to the 0 state. So this is called a bit flip operator, analogous to classical computing. The Z operator is a phase flip. It changes the phase. So you go from, it doesn't do anything to the 0 state, but it changes the 1 state to a negative here. And then the Hadamard gate will take your superposition state and convert it into a entangled state, 0, 1, and 0, minus 1 here. So you can also have multiple qubit gates. They're a little bit harder to implement and operate, especially to minimize the errors. And so on the left are classical gates, single and 2-bit gates. But here you can see the quantum gates, the qubits for 2 qubits. So you have 2 qubits here. This is a C0 gate, a controlled NOT gate, which means that you depending on the state of the A qubit, you would apply an X gate to the B qubit or not. So if it's in the 0 state, for example, then you wouldn't do anything. If it's in the 1 state, you would flip the B state. And this is an example. And then the unitary matrix is now a 4 by 4 matrix for a 2 qubit gate. Okay, so 2 qubit gates typically involve 4 by 4 matrices, single qubit gates, 2 by 2 matrices. You can also have 3 qubit gates. Here's a little library of some of the key gates. So here's some single qubit gates here, the Hadamard gate we talked about before. Here's the CNOT gate, which is a 2 qubit gate. Here's an example of a 3 qubit gate, a CCNOT gate with 2 control qubits. Here's some more single qubit gates. And here's also another schematic showing the same thing, but it nicely shows the matrix vector multiplication about how the gate is mathematically represented in terms of its operation on the qubit. So you can see some of those here. Okay, and here's a visual of that. I think we saw this before. I just like these pictures so much. They're hard to leave out of your slide deck. You can see that going from the 0 gate, applying the Hadamard puts you into the plus state. And then when you measure this state, you get 50% chance of 0 and 50% chance of 1. That's what this the squares of the amplitudes, 1 over square root of 2 would give you 50% probability. Okay, so what do these gates and circuits look like? How do we represent them? This is a circuit diagram, for example, of a particular quantum algorithm actually called quantum teleportation, which I'm not going to get into, but you can see we have wires indicating carrying the state of the qubit. So this is the qubit 0, qubit 1, qubit 2. Each qubit gets a wire, and its state changes as we go from left to right in these diagrams. So it's like reading sheet music here. And then these are classical wires, or classical bits, which are usually represented by a double line. And here's the, for example, typical implementation of an algorithm. You'd have the initialization or the reset of the quantum state to initialize the calculation. You'd apply the gates. So here we're applying a CNOT gate between qubits 0 and 1. And then we're applying a Hadamard gate to qubit 0, and then we're making a measurement. And we're outputting the measurement, and we're storing that in the classical bit shown here. And then here for the 0 gate, I'm sorry, for the first qubit, we're applying, it starts out in the 0 state, and we're applying the Hadamard gate, and then a CNOT gate between qubits 1 and 2, etc. So you can just get a visual about how these algorithms are represented in these quantum circuits, and we'll see how they're programmed in just a few minutes. Qubit architectures, the hardware, which are being developed as we speak. So it's not like we've got the computers, now we learn how to program them, and we're learning to program them and building them at the same time. So these are some of the the paradigms for quantum computing and qubit architecture. So we have superconducting qubits, definitely the most popular right now, but there are other paradigms as well. Quantum dots, color centers, which are defects in like diamonds and things like that. Trapped ions. They're also what are called topologically protected systems. There are a bunch of them. This is Google's superconducting qubit, with which in August 2019, they published a famous paper now in Nature where they claim quantum supremacy, where they've done a calculation that's basically impossible to do on a classical computer. Of course, the calculation wasn't very useful, but that's okay for now. And then China followed quickly on their heels and said that, no, they did quantum supremacy. So there's a global race right now for quantum computing. But these are some of the paradigms for qubits. So where are we now? So we're so far and yet so near. And that's tongue in cheek there. This is John Preskill, a physics professor at Caltech, who published a paper in 2018 where he famously coined this phrase, NISQ, Noisy Intermediate Scale Quantum Technology. So we are right now in the NISQ era, which implies two things. It implies small numbers of qubits, 50 to 100. I think IBM wants to get to 1,000 by next year. And they're noisy. They have error rates. A noisy qubit is like when you hit the J on your keyboard of your laptop and it gives you a K sometimes. It's unacceptable. You can't do computations that way. So we have to correct for these errors. So we need quantum error correction. It's an active area of research right now, probably becoming one of the most active areas of research to minimize these errors. So this is a nice schematic from a recent paper showing, the classical world, the desert of deathly decoherence where you can't do anything. And then you get to the verdant plains of NISQ where you can actually do some computations on a small scale noisy computer. And then if you cross the magic moat of error correction, you get into the fortress of fault tolerance where you can now use these computers reliably to do things. And so, yeah, you need like, thousands of qubits with very low error rates to get to that point. And I think we'll be there, within the next 3 to 5 years, maybe 10 years or so. This is just another infographic with the different qubit architectures and some of their error rates and who's developing what. Just included it because it looks pretty, not going to go over it in detail. And in terms of the companies that are involved, this is a nice schematic showing who's working in which space. So you've got, this is the quantum computing stack from hardware all the way up to algorithms. Quantum Machines, the company that I work for, is in control. They control the qubits, so they're like middleware. These are the big full stack providers. A lot of the names you can recognize: IBM, Google, Microsoft. But then there are some that you may not have heard of: Rigetti, D-Wave, and Xanadu. And then you've got these focus providers that are focusing on, let's say software like Zapata, or control of qubits is Q-Control, a company that I've interacted with. IonQ, the first publicly traded quantum computing company, just started trading on the market last month, or this month, actually. I'll tell you about that in a second. And these are another graphic showing some of the companies and their platforms and how many qubits they have. So the gate model was the so-called universal quantum computing model, is dominated by Google and IBM with 72 and 50 qubits respectively. Rigetti's next with 8. Microsoft is working on topological qubits. They had a little bit of a hiccup recently in the news. If you're following the field, they had to retract the paper. Intel, quantum dots. And then the non-universal quantum computing, which is something called quantum annealing, which I'm not going to get into here, but D-Wave was the big company in this. They've been in this for a long time, and they've got, thousands of qubits in this context, but it's a limited type of quantum computing. And they just announced, which I'll mention, here it is, in October 5th in the news, that they're now switching, or they're going to also build a gate-based quantum computer. And then NIST and the University of Maryland working on ion traps. Okay. So here's the quantum computing stack, as I mentioned before, with the physical quantum processors at the bottom and the algorithms at the top. And in between, you have controls, which is what Quantum Machines works on. You've got quantum error correction. I'm sorry, the controls and the readout are down here with regard to the processors. That's what Quantum Machine works on. Yeah, so these are just some more pretty pictures. Okay, so how do you program these things, right? Can you program them right now? Yes, you can. They're available on the cloud. You can get on, IBM is one of the biggest cloud providers, but Amazon is also very, very big. Their cloud providing platform is called Bracket, tied to the Dirac bracket notation I mentioned earlier. And most of the quantum programming libraries are developed in Python. So if you know Python and you know linear algebra, you can easily get into quantum computing. Knowing some quantum mechanics helps, but I don't, and so I'm all right. So you can definitely do that. Qiskit is IBM's offering. This is one of the most popular programming languages or development environments. And then Google has Cirq, and then Microsoft has Q#, based on their C#, and then there are others. And here's some examples. Here's a simple Python program written in Cirq to implement a quantum circuit. So you can see it's you import the library, and then you set up your qubits, and you apply your X gate, and then you apply your measurement operation. You can print out the data, and you can do a simulation. So there's a lot of different. This is just creating the circuit, and this is actually running the circuit. And then here's another one. I think this is Qiskit from IBM, and you can see that it's very simple object-oriented type programming at the gate level to implement these algorithms. This is another graphic with a landscape of some of the programming languages that are out there. IBM with Qiskit, Google with Cirq. Yeah, so that's that. And here's just to let you know that quantum computing is big business. Okay, so IonQ, this is from the news from October 1st. Company's going public today via SPAC offering. It started trading, I think this is October 5th, it started trading. It's publicly traded on the stock market. And then just on October 6th, Rigetti said it's going public, 1.5 billion SPAC evaluation, a SPAC deal. So this is a big business right now. And these are the first 2 companies to go public, and there'll be many, many more. I wish I had stock options in the company I did my sabbatical at, but I'm not smart enough to have asked for that, unfortunately. So I will be, not benefiting financially from this boom. Okay, let's just quickly take a quick look at algorithms, and then a few minutes on the grant, and then we can open it up to discussions. So, what are quantum algorithms? Basically, these are algorithms taking advantage of quantum power, which means we have some quantum state. We have a qubit, which is storing that state, and we're changing the state of that qubit in such a way that we're getting some sort of an outcome that we desire from our computation. And the power of quantum computing is related to the fact that we are manipulating, if we're manipulating a state of n entangled qubits, so that's the ultimate, we have n qubits and they're entangled, we are encoding 2 to the n complex coefficients. So we have basically 2 to n degrees of freedom to do our computation with. And an application of a gate on n qubits effectively performs 2 to the n computations per step. This is what they call quantum parallelism. And you might think, well, that's not such a big deal. Oh yeah, well, put in a decent number for n. You're talking about 50 to 100 qubits now. Let's say you had 250 qubits. 2 to the n is 1.8 times 10 to the 75. That's more bits of information than atoms in the universe. And this grows exponentially. So if IBM's talking about getting to 1,000 qubits next year, we better pay attention. This is going to be changing the world, basically. Again, keep in mind at the end of the computation, when you measure n qubits, you only get n classical bits of information. So the power is in maintaining that quantum state, doing the computation, and then driving the system, so to speak, so that the output gives you the answer to the problem that you're looking for. So that's what it says down here from the National Academy of Sciences. The challenge of designing useful and powerful quantum algorithms is to find tasks. So not all tasks, but find certain tasks whose operational solution can make use of this parallelism and give you a final quantum state that has a high probability, because we're rolling the dice here, of returning valuable information, which is the solution to your problem upon measurement. Okay, so this is and these are some of the classic algorithms. The algorithms came out before the qubits were built. Shor's algorithm, 1994, is famous for kicking off quantum computing because it's related to factoring large prime numbers, which is what the RSA codes and encryption for cybersecurity is all about right now. So that's why China, Russia, US, everybody is trying to work on this. Grover's algorithm, also famous algorithm, classical algorithm to do quantum search faster. And then David Deutsch, actually Israeli, born in Haifa, who has a number of algorithms named after him as well. This is an example of the quantum Fourier transform, which is depicted schematically here and is depicted very nicely in this block sphere animation that I found online. So this is a very powerful building block algorithm. And there are algorithms in all these different fields, cryptography, search, linear algebra, which is near and dear to my heart because of my interest in computational fluid dynamics. Quantum machine learning is about as hot a topic as you can. Just put together as many buzzwords as you can in a single research field, and you're going to get a paper published or a grant funded, I guess. Quantum simulation, quantum chemistry, materials processing, optimization problems. These are some of the sweet spots for quantum computing right now. And the algorithm that really, for me, touched off my interest in quantum computing is this famous algorithm, or this paper from 2009, which is called Quantum Algorithm for Linear Systems of Equations. And because in computational fluid dynamics and in science and engineering in general, that's the bread and butter for a lot of numerical computations, it was really something that caught my eye. So it came out in 2009. I don't know how quickly afterwards I saw it, but I started working on this in 2010. It's called the HHL algorithm because it's named after the authors, and the middle author, Avinatan Hasidim, is a professor at Bar Ilan, unfortunately working for Google right now, not in quantum, but and Seth Lloyd, who's a professor at MIT, a mechanical engineering professor. He calls himself a quantum mechanical engineer. I wrote a really neat book called Programming the Universe because he argued if quantum computing is computing using quantum mechanics and the universe is ruled by quantum mechanics, the universe is basically a big computer. It's an interesting concept. This is the schematic for the HHL algorithm. It involves a quantum Fourier transform. It's not a NISQ-friendly algorithm, so it's not currently useful for NISQ era machines, but it will be at some point, and it is cited widely in the literature. What is NISQ friendly, and this leads us into my grant, are what are called hybrid quantum classical algorithms. This is where you have a quantum computer doing what it does best and a classical computer doing what it does best, and they work together. The most famous class of algorithms in this space are called variational quantum algorithms, or VQAs. And this is where we have an initial quantum state, which is our initial guess of the problem we're trying to solve. We call it an ansatz, right? And we prepare that on a quantum computer. We make a measurement to get out a cost function, which is related to the problem we're trying to solve. We're trying to minimize something or optimize something. We have a cost function. And then we feed that to a classical computer and we optimized the parameters of that initial guess by applying classical optimization techniques, which are widely used in machine learning right now, to come up with a new set of parameters, which we then re-initialize the quantum circuit, and we repeat this in a loop. Okay, so this is basically like a quantum neural network, and we're optimizing, we're learning the optimal algorithm, the optimal parameters to minimize the cost function, which would be the solution to our problem. So this is a nice schematic from a very recent paper, which was actually instrumental in writing my grant when it came out on the archive last year. And this shows all the different applications for VQAs. And it is the hottest topic right now in terms of algorithms in the field. And these are a couple examples. The most famous, or the first VQA, was called VQE, the Variational Quantum Eigensolver, which has been used for finding the ground state of molecules. It's part of solving the so-called electronic structure problem. And actually, this was done by Google in a famous paper in August 2020, where they did, I think, up to an H12 hydrogen molecule and predicted the ground state energy by implementing VQE on their large superconducting quantum computer. And then my personal favorite VQA is the VQLS, which is the Variational Quantum Linear System Solver. This is the NISQ-friendly version of what HHL was trying to solve, which is AX equals B. And we've implemented this a number of times in different frameworks, and we're working with this right now. Okay, briefly, my ISF project. This is funded by the Israel Science Foundation as well as the Ministry of Defense. The acronym is HiQua, which I'm very proud of because I came up with this. You just put anything inside a Ket notation and you're really cool. But it stands for Hybrid Quantum Algorithms. And the idea is I approached two colleagues at the Weizmann Institute, Serge and Roy Ozeri, who's the vice president of Weizmann. He has a trapped ion quantum computing lab, and he has a superconducting computing lab. So normally the two of them wouldn't be on a grant together because it's like, they're competing against each other. But because I'm the novice and I'm coming at it from the application, the algorithm point of view, it actually became the strength of the proposal. So it's the three of us, and they're the hardware guys. I'm the algorithm guy, and Quantum Machines, who wrote a letter of support, is the glue that kind of sticks us together. So that's the makeup of the grant. This is the overview. We have this in the proposal. So the project is here. We have Technion on software development, and we have Weizmann on hardware development, and we're going to be interacting together. And QM with their middleware, their box that I showed you earlier with the flashing lights, is called an OPX, and their programming language, Qua, is going to be the glue that makes us work together. And I'm going to be looking at these variational quantum algorithms and also quantum optimal control, which is related to improving the performance of these algorithms by controlling the qubits with higher fidelity. And that's another novelty of the grant. And they're bringing the platforms as well. So here's a schematic from another paper that was instrumental. It was in the archive at the time in my grant, which appeared recently, which is arguing for the combination of quantum optimal control, which is trying to optimize the electromagnetic pulses that you're applying to these qubits to improve the fidelity, with the optimization problem of the variational quantum algorithm. There are two optimization problems, and they can be solved separately or more complicated, but they could be solved together, and perhaps there are gains to be achieved there. So that's the idea of this paper, and this is the idea of my proposal. Is to combine these two: pulse level control, which is what Quantum Machines specializes in, and the variational quantum algorithms, which is an optimization at a higher level. So that's the philosophy. This is just another schematic from that paper making the same type of argument. And this actually summarizes it very nicely. It says the quantum classical optimization loop associated with quantum optimal control at the pulse level is directly analogous to the procedure used in the VQA implementations at the circuit level. So this is the light bulb that when I read this, that's what pushed the proposal. If one has access to the quantum circuit at the pulse level, which Quantum Machines does, that's where I was working. They're controlling those qubits. Then you can solve the system by optimizing over the set of continuous pulses that are available. And so they're considering VQA implementations to be a form of digital quantum optimal control experiment on qubits. So it's just, you have the algorithm, which is optimal control, and then it's related to the pulses, which are being optimized. So it's just an overall optimization problem. So that's the philosophy. Okay, And what have we done so far? One of the things that I was working on at Quantum Machines was using machine learning for quantum optimal control. We were using something called physics-informed neural networks, or PINs, which was developed by my friend George Karniadakis at Brown, who I brought to Israel a couple of years ago to speak at my conference, and also deep reinforcement learning for quantum optimal control to develop optimized, smooth, short duration pulses. You want your pulses to be as short as possible before the quantum state decoheres and you lose the quantum information. And we actually ran some experiments. This is my friend Arthur, who was at the company, and there's Serge, on his qubits to do some benchmarking and test some optimized pulses. You can see the programming here. This is Roy Ozeri's trapped ion computer. It's a totally different arrangement. It's basically, you have ions and lasers and you're just keeping the ions in control. So it's a totally different type of tabletop experiment. And there's also work going on at QM on developing a quantum simulator, which is a classical computer. It's a program that runs on a classical computer that simulates a quantum computer. And you can do that either at the gate level by just the linear algebra, and there are lots of these simulators out there, or at the pulse level by solving the Schrodinger equation or the master equation if you want to account for noise. Okay, collaboration, and then we'll open it up for discussion. So basically at the algorithm level, what I'm mostly interested in, obviously, is algorithms for science and engineering problems. Solving linear systems of algebraic equations is currently the one that I'm most interested in, obviously. And it's related to other algorithms that are out there for solving ODEs and PDEs. This would have interest in across science and engineering because those are the equations that govern those physics. And then, of course, bringing machine learning into the mix. Applications that are of interest, at the end of the day, I'm always driven by computational fluid dynamics, predicting flow over an airplane. And if we can do it much, much faster with quantum computing in the next decade or two, God willing, I'll be around and we'll be able to have some fun with that. But there are other applications that are of interest within Israel. And I'm not only interested in my pure CFD applications, but things like drug discovery, bioinformatics, protein folding, quantum chemistry. These are things that I'm not an expert on, but I'm at the stage in my career where I just want to learn. So, if any of you are knowledgeable in these fields, these could be areas for collaboration. And this is just an example from a paper that I think is pretty significant. It launched a startup company earlier this year. And this is a modification of the VQE algorithm for implementing a quantum algorithm for protein folding. And if you're following the news and Google and DeepMind, this protein folding is going to change the world. The AlphaGo and the machine learning algorithms that DeepMind has come up with, and quantum versions of those algorithms would be equally transformative. So with that, I will say thank you and open it up for discussion of questions.
I'll just ask one favor, Steve. Is it possible
Yeah.
for you to send me the deck, the PowerPoint?
Sure. Of course.
Okay,
It's
so
not
if you
PowerPoint,
send
but
it
I'm
to
happy to
me,
send you a PDF. Yeah.
whatever you're comfortable understanding,
of course,
to
no
be released
problem.
freely, and that way we can circulate it and people can have a chance
Sure.
to. And also, if you would
Sure.
include on the first slide of that your contact information, so people will know how to get
Yeah.
in touch with you directly. So both people that are here now, as well as those who might not have been able to join us. Okay,
course.
if people want to jump in, you're free to open your microphones. We can take a few minutes. And if you have ideas that you want to run past Steve or that you'd like to suggest to the group, please feel free.
Who's first?
It's a lot of information to digest.
Uh,
Yeah.
Hello,
It's
thank
all
you.
pretty quick.
Thank you, Stephen, for this talk. What about communication? I mean, if you are sending a qubit over wire or wireless, what can you expect to receive in the other side? I mean, it's
Yeah.
stochastic.
That's a very important topic, Yoram. It's related to the quantum internet that China claims to have been to develop, and obviously U.S. and everyone else is working on that. It takes advantage of, for example, that quantum teleportation algorithm that I talked about before is part and parcel of any type of quantum internet or quantum message passing or things like that. I'm not an expert on it, so I don't know a lot, but there are papers out there on that, and it's an active area of research. So if any of you are in that field, classically speaking, and want to get into the quantum side, I'd be happy to do a little research with you and see if we can find the right papers to get started on. But it's definitely an active area of research, very important for military, and China is obviously doing everything these days. So yeah, it doesn't answer your question, but it is definitely an active area of research. Okay. Well, Omo, hi.
Hi, how are you?
Good to see you again.
You too. What about optimization algorithms running over quantum computers? So that I guess it connects also the machine learning type issues.
Yeah. So one of the main application areas for NISQ error quantum algorithms is combinatorial optimization problems. And there's one particular algorithm that is the most popular in the world right now. It's called QAOA, and I can share with you papers on that and whatnot. And it solves the max cut problem.
Okay.
You know that problem, I guess, from optimization. So yeah, that is a very in fact, the main application area that a lot of people are looking at is in finance. And there was a quote I think I just saw the other day from like Goldman Sachs that, I mean, they're putting all their chips into quantum right now. I mean, this is, they always want to be the fastest computing because of, trading and whatnot. But optimization and finance there's a recent review article on that. So yeah, the QAOA is one of the main algorithms, and it's actually it's one of the algorithms I'm supposed to look at in my proposal. Of course, when you have an ISF grant, they give you a lot of flexibility, which is really nice. So I'm going to reserve the right to, follow my instincts in terms of what we focus on. But in the proposal, we explicitly mentioned VQE for chemistry because I worked on that while I was at QM, and that's of interest. QAOA for optimization, and VQLS for linear algebra machine learning. So those, at least ostensibly in the proposal, are the three that I'm supposed to work on. So if any of you are knowledgeable in optimization, classical algorithms or whatnot, it's going to be a short step to get into the quantum side on that, and be happy to talk to you about that as well and share the papers.
Okay. Thank you.
Sure.
Okay, let me suggest a practical way forward if I can. Steve is going to send me, as I said, his contact details as well as the PowerPoint in some form, whether it's a PDF or a PowerPoint. I will make sure that it goes to the 15 people that joined into this meeting. I probably will not try to distribute it more broadly because I'll assume this is an initial expression of interest. I'm assuming that people came to listen, both to broaden their horizons and may have realized that there are either things they never thought of before that they're really excited about, or things that, oh, well, it's not my cup of tea. What I would suggest is that I will distribute the list of participants as well. All of you can look at the screen and you kind of know who the people are that you know. Start talking among yourselves. We'll send you the PowerPoint. Questions, for example, Steve, questions from colleagues on the business side, on the side of purely the applications.
Yeah.
The question is there a mechanism for us to bring them into the mix in some fashion where they have ideas that could benefit for simulations, but have always been told, no, that's too complicated for us to do with regular computational power. So that may be a place where, if any of the people here know of colleagues that have dreamt about simulations that were not able to do in the past, but would now like to at least consider them, I would suggest putting in a 2-line email to Steve and saying, okay, here's what can be done. Here's, is there a place here in the world of quantum computing? I'm going to wrap it here. Steve, thank you very, very much. I think these kinds of sessions, especially for an institution such as ours, where on one hand, we have a lot of highly motivated researchers, but we're a bit limited in terms of the resources, both for the lack of graduate students and because of the kind of homogeneity within the institution that we try to maintain. We need these kinds of opportunities to reach out to people with high-level expertise from other institutions. Your willingness to help is tremendously appreciated. and we will certainly be back in touch with you. I would suggest that if people want to either write directly to Steve after we've distributed the contact information and the PowerPoint, or use me as a conduit, I'm thrilled to help out in all of this. I will admit that the vast majority of both the mathematics and the computer science stuff is just like way over my head, but nevertheless, it's a kick to watch, and it's exciting to think about directions that we might go in together. Okay, thank you all very
Quick
much.
question. Quick
Thank you.
question.
All right.
Steve, did you record this?
Yeah, it was recorded. I'm hoping that the recording, even though I switched over to Yoram as the host, I'm hoping the recording will be available. I'll have to talk to people who know what they're doing. It's supposed to be sitting on the cloud, as are all of my Zoom sessions. So,
Okay, because I came late. I had another meeting, but I'd very much like to
Great.
catch the beginning. Thank you.
Aaron, I will make sure that you get Steve's PowerPoint with his contact information, and I'll try to also create a link to the recording that either people here who want to review specific things or who want to share it with those who weren't able to join in. That's certainly the objective, and that we hope will come out of it all.
Thank you. Thank you very much.
Great, thank you. All right, Steve, thanks
Thank you,
again.
everybody.
All right,
Bye.
good night.
Be well, stay
everybody.
safe.
Thank you all. Take
Okay,
good
talk to
care.
you soon.
All righty,
Bye.
Yoram, you're the on-off guy here.